started the recording. By the way, I just only yesterday I put online the videos of last Wednesday because sorry I had I forgot basically, and also I had a technical problem when I uploaded it. I had to upload it twice. Anyway, now they should be online. If you see that something is missing, let me know. Now let me share the screen. Okay, here we are. Good. So, last time we ended the lecture by talking about, one second, I want to see the camera. Okay. By talking about tipping points and the tipping points in the Earth system, as you see here, and in the social system. So here we are in the Earth system and social system. So first of all, what is the purpose of this discussion? The purpose is to give an overview of how the Earth system works, and the final target is to get the basis for understanding how models work. And therefore, by exploring first the processes, then we will introduce a theory to explain these processes, and we'll also explain how the theory translates into models. So this is why we started this discussion and emphasized the links between the different spheres of the Earth system, because of course, if we want to build up a model to represent, to simulate processes of the Earth system, we should try to reproduce it as much as possible, so as better as possible, in order to create a real digital twin, to use a buzzword that is widely used today. Why should we aim to have a model to make predictions, of course, and in particular to make prediction about future climate, and then to estimate the design variables under future climate. Tipping points are particularly important because it is something that we don't fully understand. And also they may be the reason of sudden changes in the state of the Earth system, which is a basic condition for generating the so-called surprise effect. Surprise effect is when something happens that is completely unexpected. And then we talked about the tipping points in the social system. An interesting thing, and it's still an open question, is how to connect the social system in an effective way with the Earth system. It's an open question, and that's why still the design of design projects, estimation of project variables under climate change is still a research issue. Because of course, if we want to estimate project variables, we need in a way to account for these connections between the Earth system and the social system. Basically, the Earth system is fueled by energy. We know the Earth system is closed, we said, but for the energy that comes from the sun. And it's the energy that comes from the sun that basically fuels the dynamics of the Earth system. And our target is to understand how this energy impacts the social system and what is the equivalent in the social system of energy. So, as I said, I say it again, energy fuels the Earth system. So what does fuel the social system then? And then we have to establish a connection between these fuels in order to understand how climate impacts humans. This is in a broadest sense. And the social system, we may say that is fueled by money, for instance, money fluxes. Money may be an equivalent of energy, or the social system may be fueled by something different, which is not strictly money. Okay? And so we have to understand these connections, but let's focus first on the Earth system because it's relatively simple. I mean, even if it is very complicated, when we compare these systems, Earth system and social system, really it's hard to say what is more complicated. It depends on the simplification and assumptions that you introduce. It depends also on the type of the social system, because there are many spheres in the Earth system, and some of them can be modeled more easily. There are also some different branches in the social system, different forms. Okay, so let's now move forward and try to introduce this issue of mathematical models. Again, the purpose is, at the end of the story, to estimate project variables. You will see that in most of the cases, these models are very simple. In most of the cases, they are really trivial. On the other hand, in order to fully understand the reliability of our project variables, we have to try to understand models in their complexity, how they are framed, and then we introduce simplifications. And we need simplifications because at the end of the story, we have to apply them and we have to get an estimate of a project variable. So very often in engineering, we jump directly to the final form, simplified form of the estimation model, like a probability distribution. Okay? But actually, if we jump directly at the final trivial solution, sometimes we miss the theory. You may say, why do I need a theory? Because indeed, for the purpose of engineering application, you are not strictly required to know a theory. But actually, our context is a bit different because we are working in a changing environment, and we are working with something that we don't fully know. So we cannot say, actually, in the same way as we say, I fit a probability distribution of historical data, and I think you in offshore engineering, in your previous year of master, you did that. You estimate probability distribution on observed data, and you got a design variable, a project variable. Fine. But I don't have a simple answer to say how to adapt this probability distribution with reference to the future climate. And therefore, I have to try to understand better the theory in order to understand the simplifications. So, but given that, I mean, the theory indeed is something that is not fully relevant to us, I will try to teach, to instruct you only on the basic concepts, and in order that you get an understanding of the simplifications. And I will make examples with trivial models. Okay, so just to start, what kind of models can we write? There are several different models that we can use to represent the Earth system. And there are several classifications. So, for instance, we may distinguish between what we call process-based models or physically based models. These models are based on our understanding, on a theory that tries to reproduce the dynamic of the processes by resorting to the physical laws or chemical laws. The laws that, in a way, regulate, drive the process. Like I want to describe the trajectory of a falling body. I'm fully in the void. I fully know that there is a physical law describing the trajectory in the void of the falling body. And then this is a physically based model. Keep into account process-based means it's more general than physically based, because process-based may include a chemical model. And when we study ecosystems, for instance, we often use biological models, chemical models. They are not based on physics, or maybe they are also based on physics, but they also include some laws that are not directly derived from the laws of physics. Okay, so process-based is more general. On the other hand, I think physically based is more meaningful because you know that you have to resort to the law of physics to generate the model. But the model may be empirical, and a classical example of an empirical model is the probability distribution. Empirical, what does this mean? that I try to find a model that is fitting the data, just fitting the data. I don't care about the field. Actually, when we fit a probability distribution to observe the data, we don't care about the physics. There are ways of taking into account the physics when we estimate the probability. There are ways, but in principle, estimating a probability distribution, you can do that without taking into account the physics. When I did my PhD, my advisor asked me to investigate a new branch of probability theory, let's say, a less explored branch of probability theory for estimating extreme values. And then I did it, of course, you have to do that during the PhD. And then a colleague, when he saw my thesis, said, okay, that's fine, but you could have applied it to the number of potatoes that a farmer collects from the field, and it's the same thing. That was true. I applied it to hydrology, estimating extremes, but the criticism of the colleague was, okay, but this is not really reflecting the physics. Doesn't help me to better understand the process. This is not fully true, but just to give you an idea. It's not fully true because when you estimate the probability distribution, you get some information on the underlying process, actually. And empirical models are not only probability distribution. Today, there is a growing interest, is really a huge interest for machine learning. And machine learning is random forest, neural network, and combined with deep learning. Deep learning is, I give us a very simple definition, machine learning applied to big data. Okay? And indeed, these models are getting attention because they are very quick and very efficient. And there is the problem that you need data to estimate that, a lot of data. And more data than relying on probability theory to say that, I mean. And so they are popular, but especially for the disciplines that have a lot of data available. Like, for instance, modeling internet traffic, we have a lot of data. And very often we model it with machine learning. But also in other disciplines, like modeling the real traffic of cars, they use a lot of machine learning because they have a lot of data. And for the Earth system, they are starting now. They are starting, and what they do in some of the cases to compensate for the lack of data is to use model emulators. What does this mean? They first generate the data with a physically based model, a global climate model, for instance, and then they fit a machine learning on the data that were generated. Why? Because machine learning model is much faster. And therefore, they call it a model emulator. Just, I'm mentioning it because in climate change, we listen many times talking about model emulators. Basically, they are machine learning model fitted on the on the data generated by a physically based model. Another classification, which is extremely important, is between deterministic and stochastic models. And they are mutually exclusive, but they can be combined. So let me explain. First of all, these classifications are not completely independent, meaning that, for instance, stochastic models may include the empirical models. So there are two different classifications, but of course, you may have the same model can be classified with these two different classifications, and to use a classification or another one depends on the purpose of your analysis. Okay, so what is a deterministic model? This is very, very simple, and keep in mind the definition because it's extremely important for us. And for a deterministic model, given an input and initial and boundary conditions, so given a setting of the model in terms of initialization variables, you always get the same output. So there is a one-to-one relationship between input and output. So if, for instance, I run a climate model with given initial and boundary conditions, and I run it twice, I get the same output. So there is a one-to-one correspondence, as I said, there is no uncertainty. Okay. A stochastic model, conversely, for a given initial boundary condition, you may have several different outputs. Of course, you may obtain a stochastic simulation also by using the deterministic model if you change the initial boundary condition. This is what the climate scientists do. So they understand that initial and boundary conditions have a lot of influence on the final result, like the butterfly effect, and therefore they run the deterministic model several times with different initial and boundary conditions. And then they get several different outputs, like from a stochastic model. So it is a kind of a mix. You can't say it's a stochastic model because actually the real stochastic model, also for the same initial conditions, may generate different outputs. But it's something in between, okay? And you will see many times in climate science, people talking about ensembles. What are the ensembles? The ensembles are several simulations. So ensemble means a group, okay? Several simulations obtained with different models or with the same model with different initial or boundary conditions. So you get several simulations, like from a stochastic model. Yeah, okay. Ensemble simulation is a group of simulations. So not only one, but many, obtained with possibly many different models and or many different initial and or boundary conditions. The rationale behind this idea is that we are not sure what is the best model. Okay? And therefore we use many. We are not sure of the initial conditions, and therefore we use many. We are not sure of the boundary conditions, and therefore we use many. So I get like I get an ensemble simulation, and therefore it's a possibility, it's a way to estimate uncertainty. In climate modeling, it is the norm. They don't rely on only one model. And let me just check if I can find a good link. And first of all, I want to see here if I have already some link here. Empirical models, initial and boundary condition in a reservoir. No. Okay. So if we look for ensemble simulation, ensemble. Okay, here you see many links, okay, like climate simulation ensemble. Let's see if there is some figures here. Okay, you see, this is a figure, it's a video, but let's focus on the figure. You see that there is a simulation of something, this temperature anomaly, and you see that there is not only one simulation. There is here, you see the temperature observed, and then several simulations. And these simulations are generated by the ensemble. And then you may compute the average of the ensemble, for instance, to combine the different predictions. Actually, how to combine the prediction is another complicated issue because there is not a best solution. And then there is here Wikipedia, ensemble, mathematical physics. Okay. And you see here, let me see if there is a nice video. No, because it's not related to climate. So let's forget about it, ensemble forecasting. This is quite useful. This is much used, for instance, in meteorology. They use ensemble forecasting with different initial conditions, and I don't see very nice figures, but basically you see that it's a method used in or within numerical weather prediction, but also in climate prediction. Instead of making a single forecast of the most likely weather, a set, an ensemble of forecast is produced. This set aims to give an indication of the range of possible future states of the atmosphere. Okay. And it's very simple. Basically, you make several runs. Yeah.
When we use ensembles, that ECW tools, of course, we have to respect the boundary conditions and the forecast, which are the boundary conditions we have to follow.
Usually, the weather forecast refers to a domain, and like, for instance, around a city. And basically, when you look for a weather prediction, for instance, of the 3B meteor, and you set a location, they look around that location, and they don't run the model at any time. They already run the model and the data are stored. But basically, what they do is to run a model at the local level. So they don't run for weather prediction a global model anytime. They get from the global model the boundary conditions, which means that, for instance, let's suppose that you have a globe that is this one, and you will see, we're discussing today, when you model the globe, you divide the globe in a grid cells, and then you run the global model. And but if you are interested in modeling the weather here in this one, you need to use a finer grid. So what you do is you refine the grid and run a local model called regional model. But for running the regional model, you need at the boundary condition, and the boundary condition is given at the boundary as time goes. And therefore, for instance, like typically 4 times a day, they get the boundary condition from the global model. The global model usually issues the run every 6 hours. So every 6 hours, they get boundary condition. They assume that the boundary condition remains constant for the next 6 hours. And then the boundary condition are the condition of the boundary. And then they need also for, not only for the boundary, but for each cell within the model, they need the initial condition. So for instance, for this cell here, I need to know, for instance, the temperature at time 0. Temperature, let me call it capital T, temperature for time equals 0. And where do they get this information? From a previous run, the regional model. So remember, initial condition means at time 0. And the boundary condition means at x0. X is the spatial coordinate. And we will see it in more details. So this is where they get the information. And let me just take a very quick view of the blackboard. Let me see. Okay, now it's there. And so, as you have read from the Wikipedia page, in this way, they get an idea when they make a weather prediction of the future state of the weather. Several possibilities. And this is an estimate of uncertainty. But keep in mind that this is not the global, let's call it like that, uncertainty. So it's not really the probability that the true value does not give to you the ensemble, the probability that the true value assumes a certain estimate. Why? Because the ensemble only reflects the uncertainty that comes from using different models. So basically, you may use different models and get this kind of ensemble, and we saw a graph earlier. So let's suppose that this is temperature and this is T. So you may use one model that gives to you this trajectory, another model gives to you this one. They start, all of them start from the same, maybe if you don't change the initial condition, if it's time zero, if this one is time zero, they all start from zero if I don't change the initial condition. They're from the same point at the time zero, but then they depart. And then they have completely different trajectories. And if you're interested here at time t star to get an estimate, you get this range, the ensemble range. This one is the ensemble range. So what is the true value? So let's suppose that these models are all wrong, and you don't know if they are correct. They may be all wrong. So the true value at the end of the story may be here through. So, I mean, if this was an estimate, a real estimate of uncertainty, of what we may call global uncertainty, of course, I would expect that the true value is inside the range, or maybe just a bit outside, but not very much outside. So, but in reality, this is a range that reflects only the uncertainty that comes from using different models, and it's not a real estimate of the probability, okay? And therefore, we have to be very careful when we get an ensemble simulation and it is presented like an estimate of uncertainty. We have to be very careful in evaluating how the ensemble was obtained and what kind of models have been used, because this is really a sticky problem. So very often, also in terms of climate simulations, people use different climate models and then say, I obtain an estimate of uncertainty. I see that all the models agree, so it means that I am pretty sure. But again, if the models are all wrong, the agreement between the models, it's not a real estimate of reduced uncertainty. It means that you used similar models. And actually, very often the models are based on the same principles. And therefore, agreement between models, sometimes the models are very similar. And therefore, as I said, this is a bit of a sticky problem. And this is also why sometimes in climate science, we are reluctant to communicate uncertainty. Because if we estimated uncertainty in a probabilistic sense, which means the probability of getting the true value in a given range, then uncertainty would be very large. And therefore, we are a bit concerned because if we go to a policymaker and say, okay, temperature may increase in the future, but it may also go down, I'm not really sure, the message is weakened. On the other hand, this is, as I said, a sticky debate because on the other hand, scientists should always give a true representation of the reality. So if scientists are not sure, why not say I'm not sure? And of course, it's more of a communication problem. But I'm making this introduction just to let you know that indeed there is a lot of uncertainty in climate predictions. And therefore, sometimes it's really not easy to understand it. Even if you look at the IPCC reports on uncertainty, they are a bit, and if you really look into the reports, into details, they admit it. And they say, for instance, uncertainty is estimated through consensus, which means that we interrogate different experts, a lot of experts, and they say, I think this prediction is fine. And sometimes somebody says, I'm really sure, and somebody says, oh, okay, I'm sure, but with some doubt, and therefore, based on consensus, they estimate uncertainty. But you get that this estimate of uncertainty is not an estimate of a probabilistic sense, or at least it's not verified. Okay, it's like Bayesian estimation of probabilities. Like, okay, I think that, but this should be made clear. And sometimes it's not clear. And the reason why it's not clear is precisely the fact that it's a sticky issue. Okay. Anyway, let's focus again on stochastic and deterministic, because our parenthesis started from that. A stochastic model, actually, by definition, even if we adopt same initial condition, boundary condition, same input, should give different outputs anytime that we run it, because it includes a random component. And indeed, this is sensible when we talk about the Earth system, because there is always uncertainty when we describe these processes. And here in this figure, you see a representation of a schematic representation of the difference between deterministic and stochastic models. And the deterministic is one-to-one, input and output. So, for instance, this is a sketch of a rainfall runoff model. So you get a rainfall input and you get a river flow as an output. And for the same rainfall, you always get the same output. And this is the representation of a stochastic model for the same rainfall, where you admit that the rainfall, for instance, like in this case, is maybe random, but this is not necessary. Even with the same rainfall, same numbers, the stochastic model gives a range. And this range is actually probabilistically consistent. It's required to be probabilistically consistent. And the good thing of the probability theory is that you also have the means for testing. So, I mean, when I said it should be a real estimate of uncertainty, but there are tests to check it. So it's not just my opinion, okay? The only thing is that to make this testing, and again, you need data. So when you have a lot of data, that's fine. You can make the testing, and this is perfect. When the data are reduced, the testing becomes less reliable. Why this introduction? Because indeed, there is this dichotomy in the climate modeling. So you can use stochastic models with some kind of physical basis. You can use deterministic models and maybe make them stochastic by changing initial and boundary condition or changing models. And you can use a mix. It's possible to, in a way, use a deterministic model integrated into a stochastic model. Stochastic is like a synonym of statistical. But when we say stochastic, we mean a process. So typically, the evolution of a variable given time. So what is the difference between statistical model and stochastic model? Stochastic means that we don't get a single number typically, but we get a sequence of numbers. And we are able to take into account the dependence. Okay, please.
So, model is like not by model.
Not by model.
Not one single model. I mean, the shape of color.
It's actually the rigorous definition of a stochastic model or stochastic process. We say a stochastic process is given by a family of random variables. So it's a sequence. Family means a sequence. And I said a sequence in time, but it can be also a sequence in space. And while when you estimate a probability distribution, which is a typical statistical model, you usually generate one extreme. So your target is generating one extreme, not a sequence. Usually, we don't use probability distribution to generate daily temperature data. We use probability distribution to estimate the annual maxima, to fit the annual maxima. And this is the difference. And okay, now, in a way, let's, I think we already discussed about uncertainty. Uncertainty is really relevant. I mean, uncertainty is a word that sometimes people don't like. We can also say reliability or certainty, estimate the certainty of a given model. And it is, for us, for engineers, it's extremely relevant. We cannot make any design project if we don't have an estimate of uncertainty. And therefore, when we talk about the future climate, we really need this uncertainty. And this is why I am spending time to discuss about deterministic models, stochastic model, and uncertainty estimates, because it's really important that you get it. And remember, I think I already mentioned this to you. When you get information about a climatic prediction or a climate change in general, like temperature is increased 1 degree from the pre-industrial era, you should always ask yourself or others how the prediction was obtained. So how the change, the estimate was obtained. Was it a model or observations? For temperature, it's clear, it's observations. But when we talk about droughts, for instance, which is a typical effect of climate change, or wind extremes, given that it's difficult to measure them, some people make a simulation with the models, and they say wind extremes are increased 10% since 1920, for instance. So the question that should be asked is, how did you estimate it? Was it a model or observations? And for droughts, I tell you, if you look at the models, they reconstruct the increase. So models say that droughts have increased. But if you look at the sparse data that we have, sparse because droughts are really difficult to observe, it's a long process. And the sparse data don't give us clear indication of that. For some regions, yes. For other regions, it's not clear. For instance, here in the north of Italy, there is no clear sign of drought increase in the past 100 years. There is the opposite sign. In the data, less droughts. Why? Maybe increased evaporation, and therefore more rain. Maybe.
So, what is the observation or the observation are based on the deterministic model?
No, the observation are based on a measurement. Yeah.
Measurement in models.
Yes, but I mean, the model is fitted on the measurements, and then you can use the model to generate a reconstruction of the past. But the reconstruction of the past never is similar. It's an approximation. Because, I mean, when you... Yes. Yes. Yes.
So models of observation of
yes. Yes.
Okay.
And for the example that I made, when you estimate with a model rainfall and you reconstruct past rainfall, usually the model is not calibrated over rainfall because we have only sparse observations. So the model is calibrated, for instance, on temperature, for which we have more observations. It's not it's not just a chance that the models, the climate models, are better in reproducing temperature rather than rainfall. There are other reasons, but one of the reasons is that they are calibrated for temperature. And therefore, then we extrapolate the simulation to other variables. On the other hand, it's when we compare rainfall simulated by the climate models for the past with local observations, they don't match, and neither match the statistics. So it's not just because, of course, in climate science we say you shouldn't compare the output from a climate model in a day, because climate by definition is averaged, is weather averaged over a window of 30 years. And therefore, we should compute the statistics. But even if you compare the statistics over 30 years, it's unfortunately, they are not precise. But still, the reconstruction prediction is very useful. But it should be kept in mind by an engineer that given that we have to stick on uncertainty estimate as well, there is uncertainty. And this uncertainty sometimes is not really communicated completely for various reasons. I'm not questioning the fact that it's not fully communicated. I'm just saying that we have to keep it into account. Okay, so let me just jump to here, because okay, and now there is part of this lecture. This is taken by my website, and it's the link that we opened already last week, but there is a part of it that is not given in the PowerPoint. Okay, deterministic stochastic, we talk about it, okay. Now, yeah, I want to talk of this. So, just go back to the presentation. Okay, let's forget about the presentation for a moment, and let's talk about now the mathematical structure of models. Okay, so let's focus on physically based models now. Okay, let's forget about stochastic models, because they are essential in their pure form. Stochastic models are empirical models, and they are quite easy to be understood. There is a representation, simple representation coming from statistics that is used to fit the data, and this is the essence of stochastic models. But for the deterministic models, it's important that we set the basis, and this is the kind of the theory that I was mentioning. First of all, they are mathematical representation of the Earth system, and basically a model is something that, in a very simple way, may be represented as a box, which is physically based, and this box receives an input and generates an output in a very simple form. Okay, output. And the input includes initial condition, so EC and BC boundary conditions. Perfect. And so the input may be quite complicated, because you understand that it's the input and boundary conditions may be negative. Okay, and therefore we are interested in understanding how this box is structured. So, what can be how can be constructed this box? Typically, it's a system of equations. Why a system of equations? Because both input and output can include different variables. So the output, for instance, may be given by temperature, rainfall, pressure, etc., and others. And therefore, typically, given that there are several unknowns, you need several equations. And therefore, the box is a system of equations, typically system of equations. Okay, good. Now, you may think that, for instance, I have two unknowns, and you may say, okay, at least I need two equations. Two equations are fine. On the other hand, sometimes we need to describe additional variables. And let me give you an example. For a given input, if the output that I want to describe is, for instance, river flow. Sorry if I made an open example for my hydrology, but we can easily generalize. So let's suppose that my output is a river flow. A river flow typically depends on the storage into the system that I want to model. So basically, if I want to model, for instance, the flow that I get when I pour water from a battery, okay, and the amount of water that comes out from the battery depends on the storage in the battery. If the battery is full, it comes faster. If the battery is almost empty, the flow is very, very slow. If the battery is empty, you get no flow. So, fortunately, in order to describe the flow out from a battery when I turn it upside down, not top, I need to describe what's in the storage. Okay, and the storage basically why? Because it represents the velocity with which the water comes out from the top. And in the same way, when I open the tap when I open the tap at my home, you know that, for instance, during summer, sometimes you open the tap and the flow is very slow, while in winter it's very strong. Why? Because the water supply system during summer is low level, means reduced storage. So the storage is unknown, and you need to model it. And therefore, it's an additional unknown, and therefore, even if I want to model the river flow or the water from a tap, typically I need at least two equations. One to describe storage, another one to describe the actual output flow. And therefore, here I have included in the model, inside the model, variables that are not output variables, or I'm not interested in them, so I don't call it an output variable, storage, but needs to be estimated, because storage describes the state of the system, the state of the bottom, like the bottom is empty. Clearly, storage is an indicator of the state of the bottom. So these are the state variables, what are called the state variables. And there is a link in Wikipedia if you're interested in knowing more, but I think that that's it. Just to explain that there are many equations typically in the model included, even if the unknown, the output is just one variable.
These variables are called state variables.
We call them state variables. We mean with state variables, variables that are described by the models but are not output variables. And look, for the same model, you could call the storage an output or a state variable. It depends also on the purpose of your application. But usually we call state variables those that I'm not really interested in are variables which describe the state of the system, and it's not directly the output variable. Okay? We could also turn it the other way around. I could say that the flow is an indicator of state and the storage is an output, and it depends on the application. They are related. Yeah.
Is the second equation
To describe, we need basically, typically, we need a number of equations which is equivalent to the number of unknowns, and the unknowns are the output variables plus the state variables. So basically, for describing typically the storage from a catchment, I need two equations. And let me give you an example of a model of the system. And this is a very simple example that is frequently given in order to provide something that is very understandable. And there is also the Wikipedia page. And this example is, let's see if I can, let me see if the Blackboard is included. Okay. And I think we okay. I have to remember to unpin it. Okay, let me give you another example. A very simple example is the linear lesson one. So the linear lesson one is typically a model that is used to model the outflow from a catchment from a river basin. And yeah. Yeah, no, I don't think from all they should see to the right way.
I know this. Is that like that?
So even in the recording,
basically, but sometimes professor is able to show exactly how to.
so do you see now in the Teams, are you connected? No.
But speak, we can connect with.
But I remember from registration, I see that
It's clear.
Yeah.
Because actually, I'm sure that in some of the registrations, it was okay. So, yeah, correct. I don't know if now it's pinned for everybody, and I'm not really sure if it is okay or not. But in any case, I think.
No, it's flipped.
It's flipped. So it's correct or not?
No, it's split.
Okay.
It's everything.
Okay.
It's a problem on the count.
Sorry?
It's a problem on the count that is in. Is imposted.
No, maybe.
Is it mixed?
Yeah, I understand. No, I think. I think. No, I think there is no way to. It doesn't depend on the cam. Okay. But I am sure, I know that I did it sometimes, and but I don't remember how. Let me see.
In the beginning, lectures, professor was the only one because we used to have the other classes with other professors. Professor Akemi, and it was showing like this. So I was wondering how Professor Newman was able to show.
Interesting. Let's see. Mirroring, I think.
And yeah, this is the problem. Wow.
Okay.
It was very good.
Yeah, okay. But it is a bit strange because sometimes when I attended the Teams meeting, I saw myself clicked, but people told me, no, you're right, it's okay. So, I mean, I am used to assume that not always what I see in my screen corresponds to what the others see in terms of mirroring. Anyway, now it seems okay because you checked. Okay, linear reservoir. So let me just give you an example of the linear reservoir. So what is the purpose? The purpose is I get rainfall over something, over a catchment or in a basin or over the roof of the house. I want to estimate the resulting drainage flow. Okay? River flow, for instance, or flow from the roof of an house into the pipes, into the sewer pipes. So there is a very simple approximation that is adopted to describe this kind of processes, which is called the linear reservoir. So we treat the catchment or the roof of the house like a tank with a bottom discharge. And then we assume that there is a rainfall going in, and rainfall is described by a time series. And this is actually, what is the unit of this? This is volume per unit time. So we need to express rainfall as volume per unit time over the catchment of the roof of the house. And what happens is that there is accumulation of water into the catchment, and I call it this storage. I call it WT. And the W is a volume storage. And then from the bottom discharge, I have the output, which is what I am interested in, and I call it QT. So WT is the red one is the state variable. Rainfall is the input variable, and QT is the river flow is the output. But I need two equations because I have to describe as storage, which depends on rainfall and depends on Q. So I need two equations because I have two unknowns. Okay. So how to look at this? Well, first of all, I can apply mass balance. Keep in mind, mass balance. Okay. So it's very simple. I say that. Let me write it in the black. I say that the change in storage, dWt in time, the t, is equal to rainfall minus flow. They have the same unit. Rainfall is the volume per unit time. The flow is defined by volume per unit time. And look, this is describing the change of storage. And what can you see here? This is a differential equation. Okay, and why? Because, you know, when I need to describe storage, I need a differential equation. It's clear from here, okay? But I have two unknowns because I know only PT and W and Q are unknown. So I need a further equation. And what is another equation, possible equation? I need an equation relating W with the Q, okay? Because or an equation relating W with rainfall, it will be anyway found. I need an additional equation, and the idea here is to say, okay, given that, let's take a relationship that relates the storage with Q. Why would I do this? Because I could also say there are other candidates, like I described storage in a different way. But It's clear from my conceptual approximation that the storage is related to the outflow, because if the outflow increases, the storage decreases. And therefore, the physical knowledge gives me a suggestion. Let's introduce a relationship between storage and flow. Actually, this kind of relationship in physical terms is an energy balance, because storage means energy and flow means energy. So it comes to my mind the suggestion that it could be an energy balance. But I want to make it simple, so let's forget about the theory. Let's take a simple relationship. And the idea is to say, okay, let's in a very simple way, introduce a relationship like outflow is equal to storage divided by a constant K. And by comparing the units, I understand that K has a dimension of time. It could be a multiplication, it's the same thing, but I prefer to put it at the denominator because it is more physically meaningful if this kind of constant has the dimension of time. Because it's an indication this time of the time taken by the tank to get empty, if you think of it. Okay, and so this is a very simple linear relationship. Storage is linearly related to outflow. It's a linear relationship. And what is the reason why I forgot about an energy balance? Because I very well know what is the relationship between storage and outflow from energy balance. If Torricelli law, those of you who attended some courses on electronics, it's Torricelli law, but it's not linear. So let's forget it. Why? Because people who devised this model, they work on paper, analytical computation on paper. So they prefer to use a linear relationship. Okay? And then you combine these two equations and you get your model. Of course, then what you have to do is, if you want to solve it, you have to substitute the second equation in the first one. And you get an explicit representation. For instance, you may get an explicit representation for Q. Because if from the second equation you get an expression for W, you plug the relationship for W, which is equal to W is equal to KQT, you plug it here, and then you get only one equation with only one unknown, which is perfect. Unfortunately, it's a differential equation, so you have to integrate it.
So we will substitute the.
Yes. What you do?
The orange in the first.
Yes.
Like a simple equation.
Yes, what you do is very simply, I hope it's included in the video, you get WT is equal to K QT, and then you plug it into here, and then the should be of K QT is equal to PT minus QT. And you see that here PT is known, so the only unknown is QT, and you can get it. Unfortunately, it's a differential equation, so you have to compute an integral. And by the way, the integral, if rainfall is constant, can be solved analytically. It's very simple. And what you obtain if rainfall is constant is QT is equal to rainfall constant multiplied 1 minus E minus 3 over K, if you try. And basically, again, if rainfall is constant, the resulting graph QT T is this one. If this is rainfall T, you get this. You see, when times goes to infinity, this goes to, what's that? Yes, this goes to 0, and therefore Q tends to P. If rainfall is not constant, it cannot be analytically integrated, and you have to make a rainfall integration, but it's not particularly difficult. So this is a very simple example of a model that is physically based with a pinch of empirism. The pinch of empirism is given by the assumption that the outflow is a linear function of storage. If we apply the energy balance, it would be completely physically based. But of course, take into account that even if I apply the energy balance, this model is physically based, but on the other hand, is an approximate representation of the real system. Why? Because the real system is not a tank. So if I wanted to model a tank, like a bucket with a bottom discharge, and I used the mass balance and energy balance, it would be perfectly physically based. And also the precision would be very high, because it is a very simple thing to model a tank. And if you make an experiment with a tank, with a bucket, and with a tank where you know the dimension of the bottom discharge, and you make something rigorous, but you can really make it rigorous because you take the measurement, the geometry, and the volume of the tank, the area, and the shape of the tank. You can make it very rigorous, and you get a representation with very tiny uncertainty. There is still some uncertainty. Why? Because you may remember that the Torricelli law includes an empirical coefficient, for instance, and when you measure rainfall, it's not precise. Not precise. So even if your rainfall comes from a tap that you open over the bucket, the measurement of the flow from the tap is not very precise. But on the other hand, you will see that it is the reproduction is very, very reliable. If you transfer it to a catchment, the catchment is not a tank, and therefore the measurement is and the measurement of rainfall is not very reliable. So basically, you get something that is an approximation, and this is to be expected because there is uncertainty anyway in the definition of the geometry, for instance. So if you use a bucket as the geometry, you can define it very rigorously. But think of a catchment. It is, I mean, even if you make a survey with remote sensing everything and the surveyor everything, but still, I mean, also the geometry of the river bed. There is approximation, but the model could be defined physically based, still with an approximation. And with this model, if you use, you see that it's deterministic, even if you apply it in the form of the blackboard, you use the same input, you get the same output. Okay, let me say something about K. What is K? Yes, of course, it's a constant, and it's the linear coefficient relating the storage to the output. We call K a parameter. Why? Because it is a constant which I can change in order to reach a better fit. Okay, so for instance, even if I have a bucket, a perfect bucket with everything known, but I want to apply this linear model, and therefore not an energy balance. I want to apply this empirical relationship. I have to find the best value for K. So I have to measure, to take some measurements, rainfall and river flow, observe, and I find the K value that better provides the fit for the system. This is called calibration, and K is called a parameter. So what is a parameter? It's difficult to find a definition, an agreed definition for parameter. I define it as a constant in the model equations, which doesn't change the conceptual structure of the model, but changes the fit. It doesn't change the conceptual structure of the model. This remains a linear model based on an empirical equation and a mass balance equation, but it changes the fit. So it changes, I can tune the parameter through calibration to adjust the fit. You are used to linear regression. With linear regression, what you do is you have some observations, x, depending on y, an independent variable y. Okay, you have some observations, and you want to fit a straight line in linear regression. In this case, let's suppose that it goes through the origin. Basically, the straight line, the equation is x is equal to, this is passing from the origin, a times y. Okay, this is a straight line passing from the origin. When you make a linear regression, what you do is to find the best value for a. And it's calibration of the linear regression, and in particular of the parameter slope. It doesn't change the shape of the straight line, it's a straight line, but it changes the slope in order to get the better fit. So I define parameters in this way. Keep in mind that linear system models includes parameters. Okay, now another consideration. These two equations that I used, and this is really useful example for a system model. These two equations, what kind of equations they are? So, okay, the second one is empirical, but we said it could be an energy balance. It should be an energy balance. So what kind of equations they are? They are conservation equations. Okay? And these are the ideal candidates for our climate models. Conservation equations. Why they are ideal candidates? Because the Earth system is closed. So everything but energy is conserved. And also energy, I can estimate it, the income of energy. Conservation equations. And these conservation equations, how they are applied. For instance, let's think about the mass balance. It describes the mass balance where and of what? Of the tank. So it is inside the tank that I look at the mass balance. The same for energy conservation. It would be inside the tank that I look at energy conservation. Very good. Now, the moral of the story, to be rigorous, is that you need to apply conservation equations in a volume when referring to a volume. And the volume may be like the full Earth, including the atmosphere, for instance. Okay, very good. We call it control volume. Okay, we apply the conservation equation to a volume. We call it control volume. It can move, like the Earth is a control volume, but it moves around the sun, and there is a rotation of the Earth. We need to specify what is the kind of movement that we can tolerate. And if we want to apply conservation equation in general, we need an inertial system of reference. Inertial means no acceleration. Okay? So the Earth basically around the sun, no acceleration. Okay, and the rotation of the Earth around her axis, no acceleration. So that's fine. It's an inertial system. So the control volume can move. Also, the tank moves because the Earth is moving in space. So also the tank is moving, and no problem. But the concept of control volume is extremely important. So I need to define a volume, and with reference to this volume, I apply conservation equations. So, what does it imply? if I make reference to volume. If you look at what I modeled here, it's river flow from a tank. And what does it describe? The flow from the bottom hole, from the bottom discharge. It doesn't describe the flow inside the tank. So I can't really see where the water that is flowing out, where it is coming from. So basically, here, probably, I have a movement of water. Let's take a single particle, okay, a single drop, infinitesimal volume. This particle is moving in some way inside the tank. This model doesn't describe that. Okay? It describes a kind of an average. The result comes from an average. And in particular, the river flow, or the flow from the bottom discharge, is resulting from averaging the travel of all of these individual particles from rainfall to getting to the bottom discharge. It's a result of an average. I can't describe what happens inside the average. Okay? This means that the output variable and the state variable are averaged in the control volume. Okay? Yes. The result is a result from an average. And I made the example of the outflow. The outflow is the result from averaging the travel of any drop of any infinitesimal particle. So, the model describes the output variable and the state variable averaged over the control volume. And clearly, because from here you get a number, it's Q. And if the result is you don't get any number inside the control volume. So let me extend the concept to the Earth system, because it makes it easier to be understood. And let's suppose that you want, and you consider the Earth system as a unique control volume. Okay, you describe them, you can describe temperature. I will show you why. How? It's very easy to describe the average temperature over the Earth. It's very easy. It's a simple equation, only one equation, because I don't need state variables. It comes from the sun, the energy, and is converted into temperature directly. Very simple equation. It's a balance of heat. So there is a conservation equation applied to the whole Earth. Very simple. But what if I want to know the temperature in Milan? No way. I get the average global? No way. I have to change something. So what if here I want to get the trajectory of the single particle? No way. But actually, this wouldn't be a problem if the variable was homogeneous, like temperature. If temperature was homogeneous over the Earth, that's fine. I describe the average, and I know that the temperature in Milan is the same as the average. If it is homogeneous, homogeneous means not changing in space. Perfect, it will be okay. But actually, climate is not homogeneous. What turns out is that temperature is more homogeneous. Of course, if I get the temperature in Bologna and temperature in Milan, it's not much different. But rainfall in Bologna can be completely different by the rainfall in Milan. And this means that if I want to describe temperature, okay, if not the whole globe, I could split the globe in 10 control volumes. And the description would be more or less okay. If I want to describe rainfall, no way. I need to split the globe into millions of control volumes. And keep in mind that if I want to describe river flow, I also need to describe the underground. So the control volume is not only the atmosphere. Typically for climate variables, the control volume is the atmosphere, but for the last generation of models, we need also to describe the water cycle, because climate is related to the water cycle. Basically, keep in mind that the water cycle is driving climate, and as you know, the climate scientists often say climate is driving the water cycle. I think it's the opposite. Of course, I'm biased like they are, but I mean, the water cycle is an essential component. So the last generation of models should extend the control volume in the underground because, and to the oceans, of course. And so the number of elemental volumes in which I have to split the globe is large. And the conservation equation must be applied to an elemental volume, like the grid that I depicted on the blackboard earlier. This is indeed what they do. They split the globe in a grid, and then for each grid cell, to a grid cell corresponds a volume, and they apply the conservation equations. So these conservation equations are what we need. Now, unfortunately, and I anticipate a discussion that if you look at my webpage, there is okay, a box of state variables, and we already discussed it, and there is a discussion on conservation equation, and then there is the theoretical treatment. Let's to derive conservation equations. It's the Reynolds transport theorem. I think maybe you already know it. But let's discuss it in the afternoon because it's a bit analytical. So conservation equation, let's make some examples. First of all, there are a lot of links in Wikipedia, conservation equation. Actually, most of them are a bit complicated. Okay? And because they are really treated according to the laws of physics in 3 dimensions. And I try to make them simpler. And therefore, if you follow these links, like conservation of mass, let's see, you see divergence, and okay, divergence is not really a big issue. You have a remember of divergence that is much better than mine, but there are conservation of mass is quite simple, but if you look at conservation of energy, it becomes a little bit more complicated, I think. And at least it is longer, but you see that first law of thermodynamics, it's nothing really complicated, but let's try to simplify things. But the examples that I want to discuss, there are several of them, okay? Because the conservation equation may be related to any matter that is subjected to flow. Because why flow? Because here we are describing the dynamics. So we are describing the evolution of systems. They are not just systems that are in steady state. They are evolving. The Earth system is continuously evolving in time. And therefore, you need to describe, to use the conservation equation in integral form, in the form of derivatives, differential equations, sorry, if you don't get the term. Because there is continuously exchange of storage. And if we didn't have an exchange of storage, it means that the system is in steady state, and you can directly write the equation in integral form. This is a bit complicated in words, but it's very simple if you look at here. Let's suppose that you have WT that is constant, not changing. Of course, this is an unrealistic assumption. But if WT is not changing, so this is 0, you get river flow equal to rainfall, and this is already in integral form. So you don't describe a difference. You describe the variable itself. It's in integral form. It means that it's already integrated. So, outflow is equal to rate. Like, for instance, you have a system that doesn't make any storage, like a roof of an house is very close to that. Storage is very, very small. So you can safely say, okay, Qt is equal to PT. So it's, you don't describe changes in storage and you can directly go to the integrals. But actually in the Earth system, we have to continuously describe changes in storage, like humidity in the atmosphere. And so they are expressed in the differential form. And you can write conservation of mass, conservation of energy, conservation of momentum. For instance, if in fluid dynamics, what is applied, the equations that are applied are conservation of mass and conservation of momentum. Conservation of momentum, quantità di moto in Italian, and under certain conditions reduces to conservation of energy. But momentum is more general. Momentum is conservation of momentum is expressed in vectorial form. Energy is a scalar. Okay? Momentum is a vector. And then we could also apply, for instance, also in chemistry, they apply conservation equation. And of course, for some of the matters, some of the quantities that you want to model, some of them may be not conservative. And if they are mass is conserved, energy, if it is not conserved, not always. So what you have to do is to include a loss term or a degradation term. For instance, in water quality of rivers, you describe the organic content of water, and the organic content is subjected to degradation, and therefore you have to degradation through absorbing oxygen, and therefore you have to include the loss term. So of course there are several conservation equations that you may consider, not only physics, and you have to consider losses. Mass can also be lost actually, because for instance in catchment, we assume that there is a deep percolation, some water that goes into the deep earth and maybe comes back after 100 years or 1,000 years. And so all of these losses you have to describe. And so what we are missing now is just theoretical formulation for this conservation equation that can be applied by referring to a unique concept, a unique theorem, which is Reynolds transport theorem. And then it is written for a generic variable, for a generic flux of matter, and then we can apply it to any specific matter variable. Okay, fine. Questions? I think we can take the break and see you at the 2 sharp. Okay? Thanks a lot. Yes?